Alright guys, today we're gonna talk about a couple of the problems on the homework assignment. So if we look at question 1, it reads, if the pressure P applied to a gas increase while the gas is held at a constant temperature, the volume V of the gas will decrease. The rate of change of the volume of the gas with respect to the pressure is proportional to the reciprocal of the square of the pressure. Which of the following is a differential equation that could describe this relationship? So the first thing we want to do is we want to translate this sentence into a mathematical notation. So the first thing I'm going to look at is this: the rate of change of the volume with the gas of the volume of gas with respect to the pressure. So that tells me the rate of change of volume with respect to the pressure, so dV dP, is proportional, so that tells you to put a constant proportionality to the reciprocal of the square of the pressure. So reciprocal is 1 over, and then pressure squared. So if I simplify, I have K over pressure squared. So that leaves us with a couple of answer choices. So A is out because it's just volume, not the rate of change of volume. B, you have dV dP equals K over P squared, where K is positive, so perhaps. It's the same thing, but K is negative, so perhaps. This is dP dV, so this is the rate of change of the pressure with respect to the volume. It's the other way around. It cannot be this. So the answer is actually C. Most of you picked B. The reason why it's C, and we know that K is negative constant, is because of the first sentence. It says if the pressure P applied to the gas is increased while the gas is held at a constant temperature, then the volume of the gas will decrease. So if the volume of the gas will decrease, that means that dV dP is negative. So that means it's negative, which implies, so P squared will always be positive. So that means that the only possibility to make dV dP negative is to make K negative. K is negative. So I hope that makes sense. Question 2. So in question 2 and 3, well, actually just question 2, you have to find the value of K, the constant of proportionality. So you're going to have to use some of the information provided. So it reads, the weight of a population of yeast is given by differentiable function W. So this gives you the weight, where W of T is measured in grams and T is measured in hours. The weight of the yeast population increases with respect to T at a rate that is directly proportional to the weight. So again, this looks a lot like it's telling me, hey, here's the calculus. At time T equals 10 hours, the weight of the yeast is 200 grams and is increasing at a rate of 5 grams per hour. Which of the following is a differential equation that models the situation? So before I can choose which answer it is, I need to translate this into calculus. So what I'm going to do is take this sentence. So it says the weight of the yeast population increases. So this is dW with respect to T, dt, at a rate that is directly proportional, so equals K, to the weight. So this is my differential equation. Now we're going to use this secondary information that at apparently T is equal to 10. We know that W, the weight, is 200 grams and is increasing at a rate of 5 grams per hour. So that means that dW dt at that time T equals 10 is going to be 5 grams per hour. So we can now use this information to find the value of K. So since dWt is 5 grams per hour, we can say that's 5, so we're going to keep it simple, equals you have K, and then W is 200. Grams. Oh, I forgot to put the units here. So we have 5 grams per hour. So now when we solve for K, so K is going to be 5 grams per hour divided by 200 grams. So the unit of grams cancels, and you get this weird unit of per hour. So we have 1 over 40 per hour. So don't worry too much about the units for K. They're going to be kind of weird. So I now have that the differential equation will be this: 1 over 40 W. So the correct answer is C. Question 3. A jogger runs along a straight track. The jogger's position is given by a function p of t. So we know that position is p of t, where t is measured in minutes since the start of the run. During the first minute of the run, the jogger's acceleration is proportional to the square root of the time since the start of the run. Which of the following is a differential equation that describes a relationship where k is a positive constant? So, most of you chose the answer that looks correct, which is A, but it's actually C, and it's because of this very simple fact. So position is just p of t, that means velocity is p primed of t, which is the same thing as dp dt, and then acceleration is p double primed of t, which is d squared p over dt squared. So that's the second derivative. So that means that to translate this sentence correctly, it says the jogger's acceleration, this is acceleration, the second derivative of position. So I'm going to write d squared p over dt squared is, so that means equals, proportional to the square root of the time since the start of the run. So the correct answer is indeed C. So a lot of you got this wrong because you didn't take into account that dp dt is just the velocity of the jogger, but it's in fact the second derivative of the position that gives you the acceleration, and that's why it is answer choice C. So I hope that these three problems made a little bit more sense. These three problems were missed by a lot of people, and I think it's just because of silly mistakes, especially number 1. That one was kind of tricky to get your head around because a lot of you picked which one would be B, okay, but it's actually C, and you know there's a very simple reasoning for that. Number 2, you just had to find the value for K using the given information. Again, I wouldn't spend too much time trying to understand what the units for K are. They're usually going to be very weird. And then question 3, it just you had to think about that the acceleration is the second derivative of the position, and that's why it's d squared p over dt squared. Well, I hope that helps, and if you have any questions, please send me a message.